Gonna get started. So thanks everybody for coming. We have a great pleasure to have Professor Sarah Gallagher from Western University in our midst today. So Sarah is also the director of the Institute for Earth and Space Exploration at the Western University, and her research is focused mostly on supermassive black holes at the center of distant galaxies, as well as compact galaxy groups. And she's made use of observations across wavelengths to study these objects. Sarah received a PhD from Penn State University and then had postdoctoral stints at MIT and UCLA before joining as an assistant research astronomer at UCLA, after which then she came to Western and joined as an assistant professor. Sarah is also the president of the Canadian Astronomical Society, CASCA, and she was also the first science advisor to the Canadian Space Agency. So Sarah, thank you again for coming to CITA, and Sarah will tell us about cautionary tales from the local universe.
Thank you, Aditya. And it's my pleasure to be here and share this talk with you. I gave a condensed version of this talk at a conference in November, which was focused on some of the real new and exciting results, particularly that are coming out of the James Webb Space Telescope on the early universe. And so my motivation here, particularly to a community of theorists, is to give you some skepticism for some of those results, so you don't spend weeks and months of your life trying to come up with explanations for results that may not hold up under further scrutiny. So really, it's a service to the community. That's the plan. So, oops, there we go. All right, so this is an example of some of what James Webb Space Telescope is showing us that we have not been able to see before. So here is a graph. So this is redshift, and this is bolometric luminosity on the y-axis here. And so what you can see is this: these brown contours are the population of active galactic nuclei that were known previously. And then all of these colorful symbols here, the blue symbols, the stars, and the diamonds, are some of the new active galactic nuclei that are being discovered with the James Webb Space Telescope. And you can immediately see that two things are really fantastic. One, we're pushing to much higher redshifts, so beyond 8, which is very exciting. And then also we're able to probe to much lower luminosity. So this is getting to a population that really was just not accessible before Webb. And what Webb gains us is we're looking at longer wavelengths, and we also are able to have much greater sensitivity. So that's the sensitivity is what is getting us down to the lower bolometric luminosities, and then the longer wavelengths help us push out to longer redshifts. So this is a very exciting population of new objects, and there are a couple things that have been revealed that were surprising. At least surprising to a lot of observers, though I've heard from the theorists they weren't surprised at all. So
they never are.
Yeah, anything is possible. So one is there's more than people were expecting. They're being found quite easily and quite frequently. And the other is there's some evidence that they have relatively large black hole masses. And some of them are also being found in quite small galaxies. So these are things that are a little bit surprising, and I just want you to keep those in mind. This is part of the framing and the motivation for what I'm going to be talking about. So one thing I also want to mention is that you can think of an active galactic nuclei, quasar, the most luminous ones, is basically just something that happens to a galaxy. It's not a weird thing, it's just something that happens. It's a phase it's going through. And this is one of my favorite examples of surprising and weird things that have been discovered in the universe. This is called the Hanny's-Bohr work. And so what you have here is you have a completely normal-looking spiral galaxy. It's just kind of minding its own business. And right next to it is this giant, like scary-looking green cloud of gas. And it turns out that the reason this is green is because, and this was discovered through Galaxy Zoo in the Sloan Digital Sky Survey, the reason it's green is because it's basically emitting all of its energy in O3. At 5007 angstroms, and it's a big cloud. And the best explanation for this weird looking thing is that this was an AGN, and then that photoionized this gas, and then the AGN turned off. So we have no evidence for it anymore in this galaxy, but we know it happened because of the impact on its environment. And so this is just to remind you that being an AGN, an active galactic nucleus, is something that galaxies just do at some point in their lifetime. It's not a different class of thing, a different class of object. So if we think about these redshift 6 to 10 quasars, and we want to have, if we want to come up with local analogs, and of course the reason you want a local analog is because it's a lot easier to study things that are nearby, because they're larger on the sky, you have higher signal to noise, you have better spatial resolution, so it's really useful to be able to do that. But we have to then make sure that our local analogs map well onto those high redshift objects we want to study, and also recognize the limitations for the local analogs we choose. So if we say redshift 6 to 10 quasars, where are they now? We expect that they are in the most massive galaxies. So this is M87, the central dominant galaxy in the Virgo cluster. That could easily have been a quasar, an active galactic nucleus at redshift 6 to 10. And of course, we know that there's a big bad supermassive black hole there because of the Event Horizon Telescope. So that black hole had to grow at some point, and it had to grow a lot. And so it likely happened in the early universe, at least some part of that growth. And then also remember that the most massive galaxies are also in galaxy clusters. So that's where they are now. But then, of course, they weren't in massive galaxies and galaxy clusters at redshift 6 to 10. So we have to go back and figure out where they were. So if we look at this is an example of a merger tree. So, and this is going forward in time here. So each one of these little stripes here represents that initial seed to a galaxy, and then moving forward in time with hierarchical structure formation, all these different seeds are coming together and merging, and then we wind up with the biggest, baddest galaxies. This is a theoretical merger tree for a brightest cluster galaxy. So we go back to redshift 6, so that's 13 gigayears ago, and we have a bunch of little things like this. So we're looking at things that are relatively small in terms of the stellar mass. The color represents the color, the size represents the mass in this. And then we say, okay, going back in time, what do we need to look at things that are less massive, so the stellar mass was different. Another thing that was different, of course, at higher redshift is the amount of cold gas and the gas to stellar ratio. So this just shows, these are two mass functions. So this is the number density per unit volume. This is at redshift 0, and this is for the CO, the molecular gas mass in a galaxy. So you see a typical luminosity function. There aren't that many massive things. There's lots of lower mass things. This is at redshift 0. But at redshift 2, you can see that this mass function extends to much, much larger masses. And of course, that makes sense. We expect that molecular gas gets consumed over time. And so we have a lot more stars now than we used to have. And so there was a lot more gas in the early universe. And the other thing that changes for galaxies is their kinematics. So the stellar mass obviously increases over time. The cold gas mass gets consumed and converted to stars or becomes heated. And then the galaxy structure and kinematics also change. So this is just a figure which represents our galaxy, the Milky Way. So this is the number density of stars per 10 parsec cubes as a function of the height above the disk. And so if we look at the population of low mass stars, G and K stars, they're probing the thick disk. And from Gaia results from Jiang and Ricks, they put the formation of the thick disk at something like 13 gigayears. So the kinematics are much hotter in the early universe, and we have to also keep that in mind when we're looking for local analogs. So we might look at something like this. So this is a rendering from Gaia of the Large Magellanic Clouds. So this is taking all of the data and making a model. It's not an actual image, making an image. It's not the actual image. And so our low-Z analogs for galaxies that might be hosting the seeds of black holes relative to what we see in the early universe, they should have relatively low masses, so less than 10 to the 9 solar masses, very high gas fractions, and they also need to be kinematically hot. You can't have nice, well-organized disks. We don't expect those to be able to form in the early universe. And so I'm going to give you a cautionary tale about what we need to keep in mind when we look for those kinds of systems. And this system, I think, is really, really interesting. So this is so what I want you to do is, first of all, just focus on the contours. So this is the contours of the 21 centimeter emission from a system which is called UGC 3672. And here, this shows the contours of the density. You can see it looks kind of disc-like. And then these represent the contours, the velocity contours. And this definitely looks like a disk. The kind of thing, if you're looking at an edge on disk, you can imagine the intensity contours might look like that. The velocity contours might look like this. But this is actually 3 galaxies. So if we're thinking about what we think is going on in this system, if we only had the H1 or we only had the image, we would not necessarily guess that those two things go together. And particularly at low resolution, if we only had this 21 centimeter, we would think this was a single disk galaxy. But in fact, it's 3 dwarfs that are likely, these are 3 little dwarf galaxies that are likely in the process of merging. They still have a ton of gas. You can see the gas extends way beyond the stellar disk, and the gas fraction is quite large. Excuse me. And it looks like it's an organized disk. If you have higher resolution, higher angular resolution, it starts to break up a little bit. But at low resolution, you might just interpret this as being a single disk. This is actually an oversimplification of what's happening in this system. So this is just something to keep in mind when you think about what you may have heard of as little red dots that are being discovered by the James Webb Space Telescope, is there might be a lot of complexity that's hidden at different wavelengths or with higher resolution, higher spatial resolution. Now here is, I have this is the audience, the interactive audience participation. So here is an image of what's called Hickson Compact Group 31. I want to ask you, how many galaxies are in this image? Okay, I'm just going to start counting, and if you think that's the right number, then raise your hand. 1 galaxy. Nobody? 2? No? 3? 4. You think 4? Okay, 4? Okay. More? 5? 5? Definitely 5. Okay. Anyone else? I mean, how many?
You mean like the whole thing?
The whole image, yeah.
Like 11?
11. Okay. So it's hard, right? Like just looking at this image, and this is a particularly interesting image. This is a Hubble Space Telescope image. You can see, I don't know if you can see from the back, the colors are weird. Like this looks really green. This looks kind of purple. So the colors are weird. The other thing is there's some background galaxies. This is a background galaxy. That's another background galaxy. So the galaxies that are actually in the system that we think are interacting, there's 4. And so this system right here is actually 3 galaxies. And so our best understanding of the explanation for the way this system is right now is that this galaxy C actually swept up past galaxy G, left a bunch of tidal debris here, which then collapsed and started forming star clusters, and then sort of smashed into A and B, which were already kind of colliding. So this is a collision of 3 galaxies, chances are. It's not totally clear what's going to happen afterwards, because depending on the actual velocity vector, C could just keep going, or maybe there's enough mass here for it to, eventually merge, and you could have these 3 small dwarf galaxies merge into a single galaxy. So I just want you to keep in mind that this is complexity that we see in the local universe within 100 megaparsecs. And if we just saw the little tiny image from the James Webb Space Telescope at 2.5 microns, we might basically underestimate the complexity in the system because we don't have all the information that we have in this particular system. And the other thing that makes this particular system a good low redshift analog, so it has disorganized, I'll just go back to this image. I mean, this is a relatively reasonable disk. I mean, those are messes, right? You wouldn't think that those are nice, organized spiral galaxies. You can see there's a lot of star formation, and if you look at the gas, it's very gas-rich as a system. And the other thing that is happening is that these clusters, these are sort of clusters of star clusters that are recently formed. They're very young. They're called complexes, and they actually have sizes that are comparable to what are typically seen at redshift 1. So this really is a nice local analog, at least to redshift 1, maybe not all the way to redshift 6, where we have lots of gas, it's low mass, the whole system, if we added all these galaxies together, is about the LMC mass. And lots of gas, very disorganized, and it's hot. It's kinematically hot, and we know that because these star cluster complexes are large, are physically large.
Can
So-
I ask a question?
Yes.
A couple of times now you've talked about lots of gas.
Yes.
So can you give that to me like as a fraction of the, I don't know, the stellar mass? Like, are we now talking,
Like
we're
10
dominating?
times.
Thank you.
Yes.
Perfect.
Any sign of a black hole?
In this particular system, no. Yeah, but it's a little hard to tell when you get with these low mass systems, even if you have, for example, an X-ray points, I mean, where's the center of the galaxy? I'm not totally sure. And then also the luminosity of some of the X-ray point sources would be comparable to a massive X-ray binary. So there's no one has claimed that this is an AGN, but it'd be pretty easy to hide one. All right, so I'm going to give another example. This is Cautionary Tail 3, and this is looking at Higgs compact group 16. This is one of my favorite Higgs compact groups. These groups are really interesting because you have a small number of galaxies. They're physically very close together, but they're relatively isolated. So that means that you can really trace the individual dynamical interactions and in a way that gets lost when you have comparably dense environments, for example, in clusters. So here are 4 different galaxies. This is the Hubble Space Telescope image of them. And I put labels here that indicate what their spectral types are. So we have a group of 4 galaxies, and they are all active in some sense. They're not broadline active galactic nuclei, but we have a Seyfert-2, 2 liners, and a starburst galaxy that is a luminous infrared galaxy. So that's what we see in the optical. Now, if we add in the infrared, and this is from Spitzer, the Spitzer Space Telescope, what you can see is that the starburst galaxy is actually saturates the detector. It's incredibly luminous, and each of these is a bright infrared source as well. And then if we look at the 21 centimeter emission, so these are the contours that indicate where the cold gas is. You can see that there's evidence from this cold gas, even though these galaxies look relatively well behaved, this is still a nice spiral. It's got strong arms, so that's indicative of an interaction, but they're not obviously merging. But then you can see there's this shared H1 envelope, which indicates that they have some history of interacting, that they have been able to share some of their H1. And then also, if we look at these in X-rays, you can see that this is an X-ray emission, that all of them have nuclei that are bright in X-rays. So figuring out how these objects are interacting, you really kind of need to do the census of all of the baryons and all the different phases in order to figure out what the interaction is. Yes?
Just in terms of the alignment of those, is it true that the starburst does not have any H1 emission, or am I understanding that?
This is the starburst here. This is an extra galaxy.
Oh, okay.
It's actually right down here.
Okay.
This is the
Yeah.
Spitzer. So that's the starburst.
So good.
Yeah. So it still has some H1. And so one of the ways that, let me just step back again. So we'd like to understand systems like this, as well as other Higgs compact groups. So how do you wind up with 4 galaxies? And these are more massive than the ones I showed you before, which were all dwarf galaxies. So we have 4 galaxies. They're basically all active at the same time. That activity was likely triggered by interactions, but they are not currently merging, because if you looked at these 4 galaxies, they do not look like merging galaxies, merger remnants, but they are clearly interacting. And our best understanding of this particular system is that this is represented by this graph. So what this is position in 3 dimensions right here. This is from a simulation. This is not a simulation of this system, but a simulation, but a system that was found in a simulation And this work is Sanaveris et al. We're looking for redshift 0 systems that look like Higson compact groups that we know and love, and trying to understand their evolution and how they wound up where they were. And our best understanding of this is that what each of these represents is the path of the galaxy through space over time. And so what we think has happened with something like HCG 16 is we basically had 4 separate galaxies that over time were sort of on a collision course, and now right around redshift 0, they've actually sort of all come together. And so they have, the reason we think this has only happened recently is the galaxies don't look really disturbed. They still have a lot of gas, but the gas now is in a common envelope, so they're coming together in some sense. So this is one potential path that would lead to the evolutionary situation that we see today. And one of the reasons I'm going to show you an alternate path that we think represents a different system is that in this case, these galaxies are basically just minding their own business for gigayears, and then they eventually come together in the local universe. Now, this is in contrast to some of the other Higson compact groups, which show evidence for evolution, but not for mergers. And so that is represented by this diagram, which again, so this represents 3-dimensional, like a cube of volume. Each one of these tracks is all of the precursors that led up to today's massive galaxy. And so if instead of having galaxies that just all come together at redshift 0, instead they are traveling together along a filament, you can actually have a compact group that's quite long-lived if their velocity vectors are more parallel. So they're sort of dancing around each other, and you can see that happening right here. And these galaxies are not going to merge, but they are going to interact with each other and cause galaxy evolution over an extended period of time, but it's not a merger. So I think this type of evolution is perhaps underexplored in general, because I guess it's more fun to crash galaxies together. But this is something that I think is quite interesting, and we do see evidence for these in Higson compact groups. Yes?
Yeah, thanks. I'm just wondering, the previous scenario you have where like the 4 galaxies basically interact with all together at roughly the same time.
Yes.
It seems like a low probability event as opposed to like 2 galaxies interacting and then 2 galaxies interacting. Like, do you have demographics for how often you get like a 4-body interaction versus just 2-body interactions from surveys?
Let's see. So offhand, no, but it's also like, it's not a totally easy question to answer. So the Higson compact groups are relatively rare systems. So, and they were historically discovered in lots of ways that are, so for example, in the Sloan Digital Sky Survey, there have been various surveys of compact galaxy groups, but there's a limit to how close you can put Sloan fibers together. So actually that number could easily be underestimated. And the other thing as well is that once you get beyond the local universe, a lot of the galaxies, which might be lower mass, are just going to drop out of your selection. So I think our understanding of these kinds of systems is incomplete, but certainly they could absolutely be rare. And for something like HCG 16, all 4 of those galaxies are luminous, so they're really easy to find, but they're also quite rare for that reason. Did that answer your question?
Yes, thank you.
Okay. Okay, so now I want to talk about Stefan's quintet, which is my favorite Higson compact group. And this is a really extraordinary system. And part of why I wanted to bring this up as the 4th cautionary tale is just to remind you that really weird stuff actually happens in the universe. And the weird stuff that is happening in this particular system is that we have, and I'm just focusing, it's Stefan's quintet. So there's 5 galaxies. I mean, this was identified in the late 1800s. That's what the name is for. But I'm just focusing on these 3 galaxies right here. This is a pair of galaxies, and then this is another galaxy. And then you can see, and this is a James Webb Space Telescope image. The red is from MIRI, so that's mid-infrared. So you can see these weird, kind of creepy, glowing fibers. And this is all emission from molecular hydrogen, which is hot, and so the vibrational modes of molecular hydrogen have been excited, and there's also polycyclic aromatic hydrocarbon emission as well. And so what's happening in this system that's quite extraordinary is that, I mean, clearly this is an interaction, a very strong interaction. And you might think, oh, that's going to be a merger, except that this galaxy right here is actually coming from behind at 900 kilometers per second. There's a big cloud of gas here that was deposited in the intergroup medium because of a previous interaction. And so there's gas outside of the galaxies that this galaxy is basically smashing into. There's a huge shock. It's 50 kiloparsecs long. It's causing a huge amount of star formation. And this galaxy is moving at 900 kilometers per second, and it's not clear that it's actually bound to the system because it's moving so fast, and this is a relatively overall low mass system. So this may be a temporary situation, and this galaxy will just leave, and it'll be a big mess right here. And but it's like a hit and run. It could leave the scene of the crime, and you would never even know it had been there if we wait a year or something like that. So this is just to remind you that these sorts of things do happen, and we don't necessarily always have, when we're just looking at a small piece of the sky, we don't necessarily have all the information we need to figure out what's going on. And in this particular system, we also have, we have these starbursts that are happening outside of the galaxies. This is an active nucleus, and then we do have this big shock that is basically emitting in any wavelength you can think of. So I'm now going to zoom in, and I hope you can see this in the back. There's a whole bunch of these little dots right here. So these are individual star clusters, and when we have individual star clusters, the nice thing that we can do is we can look at the light from the star clusters in lots of different bands, and then we can fit the spectral energy distribution of that light, and we can get ages and masses and the dust extinction to each individual star cluster. Now, what's great about these star clusters in terms of these types of systems is the star clusters are born in triggered star formation, and so if we can age date the star cluster, then we can figure out when the different dynamical interactions happened. So, and also I just want to remind you, again, thinking about that early universe, is that the James Webb Space Telescope is using gravitational lensing. So here's an example of a lens. You can see all these bright, I love all the names they have, the firefly sparkle and cosmic gems, and all of these bright little point sources that are individual star clusters that are being found with ages, redshifts from 10 to 6. And so understanding star cluster formation, particularly in these exotic environments, could be quite powerful in terms of understanding what's happening in the early universe of galaxies. So this is work by Aramel Panthayapura, who's a postdoc who is working with me at Western. And so what this is log of the flux on the y-axis. This is wavelength in nanometers. And I've asked, this is unpublished work, so please don't take pictures and tweet them until Aramel has a chance to submit his paper, which should be very soon. And so what this shows in this plot, we started off with, this is a single star cluster. These crosses are all of the photometry. We've been working on Stefan's quintet. I've been working on it since 1999, so I really, really like this galaxy system. And so we started with HST data. So we have from the U band to the I band. So that's about 300 nanometers to about 800 nanometers. And then James Webb Space Telescope, we're adding in all of these different bands. And then what this shows is that when we add the James Webb Space Telescope, we get a lot of diagnostic power. And we were able to discover a couple things. So the orange curve right here is the fit of the star cluster when we only had the HST data. And then we added in the James Webb Space Telescope data, and then we get this curve right here, which is this blue curve. And what you can see is these in particular really showed that our previous fit was completely wrong. And we were able to discover two things. One is that when we're with the additional wavelength coverage, we have PAH emission, and we also are sensitive to the emission lines here. And the other thing that we discovered was that this U band right here The older age fit better to the U-band data, but we think it's because the dust, it's different kind of dust. It's not the normal ISM dust. There's different dust in these young star clusters, and so that needs to be taken into account. So, adding in the James Webb Space Telescope data told us we got the ages of the clusters wrong. And then if you get the ages of the cluster wrong, you also get the masses wrong quite significantly. So in this isn't a huge deal. Some of them are more dramatic, but so we had 10 to the 6.8 is the new age, log of 10 to the 6.8 years. The previous age was log of 10 to the 7.86. And so with our new fit, the age is younger, the extinction is greater, and the mass is less. And so the mass is less by a factor of 3. And I just want you to remind you that the James Webb Space Telescope data that we have now that's doing such a fabulous job finding young black holes and also star clusters in the early universe and lensing arc is probing the rest frame optical. So it's the same sort of data that we have here with HST, and then this is just, I think, a really nice example where getting the rest frame near infrared is actually very powerful, particularly for these very young clusters. And then this just shows, is there a question? Yeah.
So you have to assume a certain range of IMF.
Oh, yes, yeah, absolutely, yeah. So that's certainly another point. We are assuming initial mass functions that we're familiar with, and if they're wrong, then all bets are off for the masses. But even just getting the ages wrong has a really significant effect in the mass, even if you, with the caveat that we don't really know what the IMF is. So this just shows a histogram of all of the objects that we have. So when we have the HST plus JWST, that's the orange curve here, and this is just showing you that, so this is age, so we have a lot more young clusters in the orange there. With just HST, we had a lot more extinction 0 values, and then they're getting redistributed to higher extinction. That's what this represents. And then this just shows the mass here. And so the older ages are giving us much bigger masses with this blue histogram here, and then the revised ones are quite a bit smaller. So these are, so we're really getting the age wrong has quite a significant impact. This is now, I mean, you probably can't see these right here, but this is 100 objects that have been relocated in terms of where they are.
So not to go too far with it, but it basically says that when we're doing it in the optical, we're underestimating our uncertainty by a huge amount because you didn't actually change anything in the optical, so you had the same data.
Right.
So you could have predicted the other one as a possibility, but you didn't. Right? So it's really saying to us, like the most important thing from a sort of Bayesian perspective is there's a lot more parameter space there that we should be looking at, and all of these should be taken with a giant, like it's your grain of salt, right?
Yes, for sure. And I will say that so if you have older clusters, the adding James Webb doesn't really change the ages very much. But with the young clusters, especially if you don't have your extinction law right, you can be off. And it is significant. It's factors of a few. It can definitely be factors of a few. All right, so I'm moving to my so shifting gears a little bit from Higgs and compact groups, and now I'm going to be talking about the AGN, active galactic nuclei, in small galaxies that have very massive black holes. You may have heard of these as being characterized as little red dots. And they're little red dots because they're basically unresolved in James Webb Space Telescope, and they have a red color. And they also, and I'll show you what some of the spectra look like. So from the spectra, there have been estimates of the black hole masses. So what this shows is this is just the absolute magnitude in the ultraviolet. This shows the mass of the black hole. The little red dots are all of these red stars here. And then this is the bolometric luminosity. So you can see they're quite high. This is definitely in the quasar regime, 10 to the 45, 10 to the 46 ergs per second. And the mass of the black hole here is between 10 to the 7 and 10 to the 9 solar masses. And these are objects that sort of start at redshift 6. So these are quite extraordinary. How do you get black holes that big when the universe is less than a gigayear old? That's a question. And the other thing is they are in galaxies that look very small. So sort of less than a kiloparsec in terms of the size of the galaxy. And those are two really big puzzles about these objects. And I just want to show you what the spectra look like. So certainly there is no question about the redshift. So there's multiple emission lines. They look like they're supposed to. And so this is Lyman alpha right here. This is H beta, this is oxygen 3, and then this is H alpha right here. So there's no question about the redshift. But I just want to focus on these zooms here. So this is H beta, and this is oxygen 3 here, and you can see the fits are these dashed red lines here. This is H alpha, and remember the black hole masses are measured from the width of the emission line. So I just want you to keep that in your heads. Oh, and the assumption, of course, is that the gas is virialized, and that you're actually capturing what you think you're capturing in terms of the correct element that you're seeing. So this is just to show you the data that they're working with. So absolutely no question about the redshift, but I just wanted to show you what the data looks like that is being used to measure the black hole mass. And so now I want to talk about my fifth cautionary tale, which is actually when we have beautiful high signal to noise data of a local AGN, Markarian 142. This is the thesis work of Vierge Katu, who's now at the Canada-France Wide Telescope. And these are Gemini spectra of a campaign to look at Markarian 142. So we had a beautiful 8-meter telescope looking at, it's a Markarian object. Those are pretty bright. They were discovered in the 70s. And, excuse me. And so we have very beautiful high signal to noise, and she looked at it repeatedly in order to, we were doing a reverberation mapping study to measure variability and get the black hole mass. And so here is the H beta line, and this is what's called a narrow line Seyfert 1 galaxy, which means that the emission lines are intrinsically narrow. And then here's the oxygen 3, and what this shows down here is what else is going on in the spectrum right around H beta. So this, some of the things, all of these bumps and wiggles here these are fitted. So narrow line Seyfert 1s are known for having strong iron 2 continuum. And there's so many iron 2 emission lines that they just kind of blur together into what's called a pseudo continuum. And there's a helium 2 line right here. You have your O3. You can see that the iron 2 has peaks in between O3 and H beta. And so you can see that this whole region of parameter space is quite complex. And when you are measuring the broad line, you need to subtract out the narrow line component, because when you get a black hole mass, you want to probe the gas that's actually orbiting the black hole, and the narrow line region gas is not orbiting the black hole, so you need to subtract that out. And you also need to account for the iron 2 continuum. And so this just shows the difference between Gemini spectra with resolution of 186 kilometers per second. And then this is a spectrum from the Lijiang telescope, which has a resolution of 695 kilometers per second. And so I'll just give you a moment to look at this, and in particular to focus on this and this. And so what you might be able to sort of eyeball is that if you have low resolution data, the lines look broader. And the reason they look broader is because of, let me show you. The reason they look broader is for two reasons. One is that when you have this iron 2 emission, the broadening the spectral resolution basically puts more power into the wings of the H beta line. And the other thing that happens is that now you cannot tell the difference between the narrow line and the broad line. When you have higher resolution data, you can see there's an inflection point out there, and so it's a lot easier to figure out what the narrow line is and subtract it out. But when you reduce the spectral resolution, that becomes impossible. So both things together mean that it is much harder to actually extract the appropriate width of the emission line. And so then what happens is this is what happens. So we have the, what this shows right here, this is the ratio of the iron 2 emission to the equivalent width of the iron 2 emission to the ratio of the H beta emission. And then this shows the full width half maximum of the H beta emission. And so what you see is that the, let's see, this is the low resolution, this is the same object. This is the low resolution data. Each one of these data, this is a variability study, so we've looked at this object again and again and again, and each one of these is an observation, and then this is the high resolution data, the Gemini data. And so what you can see is with Gemini, we measure the iron 2 emission as being quite a bit stronger. The full width half maximum is a lot lower. So this is about 1,700 kilometers per second. Whereas with the low resolution data, we're underestimating the contribution from the iron 2 emission, and we're getting a much broader line, which is about more like 1,900 kilometers per second. And I just want to remind you that when we're calculating a black hole mass using a width of an emission line, it goes in as the square. And so if you have overestimated the width of your line, you're going to significantly overestimate your black hole mass as well. And so that's, and so this is my sort of fifth cautionary tale.
Just like as a Bayesian, could you just like figure out the fudge factor and just fudge all the various observations? Like, is there any, I mean, could you propose a study like this where you basically just correct? Or do you think that there's enough uncertainty individually in each object that that would just be a bad idea?
So I'm just going to go back to the actual spectra, right? And I also, I don't want to say that they got them all wrong at all. Like, I'm not saying they did a bad job or they got them all wrong or anything like that. I just want to say that, you know, there could be complexity that's being hidden. So the, so you could, and also, so what, if you see the difference between these two, so this object has almost no O3 emission, and this has quite strong O3 emission. So this is the sort of thing that is, you might be able to calibrate it out, but you'd have to have sort of multiple parameters. So for example, if O3 is thought to be completely narrow, so if you can measure, so that can help you measure the width, the unresolved width. But when your ratio of O3 to H beta is so variable, that's a little tricky. And also, I mean, who knows how much iron 2 emission there is at redshift 6? I mean, there is iron, it's been detected, but what we observe in the local universe, that calibration might be a little bit tricky. And these galaxies in particular, the little red dots, have a continuum contribution from galaxy as well as from the active galactic nucleus. So I think you could probably use the sort of diversity we see in the local universe to maybe do a better job with uncertainties, but I think it'd be quite challenging actually to calibrate it out. But certainly getting higher resolution spectra, at least for some of these, would be worth it, just to see if at least to subtract out the narrow line emission. I think it'd be hard with iron 2.
But degrading the nearby stuff to see just how bad it does would probably be useful, at least to try to give you for your next slide where you showed how bad it.
Yes.
Right? So at least that's something you can do right to begin with.
Yes,
right?
That's
because
true.
For the example you give, it's only about a 30 or 40% in terms of velocity, which means only going to be a factor of 2 in terms of mass, like because of your squared.
Yeah.
So that's not like, I thought these values were so large that it was more than a factor of 2 that they were worried about the black hole masses. Maybe I was wrong, that they were so high. I thought it was more than a factor of 2 that they were saying that these things were large.
Right, yes. That, so the discrepancy does seem to be a bit larger.
Yeah.
But
The
okay, just to be completely honest, I don't believe any black hole mass beyond like redshift 1.5.
Yeah.
But
I agree.
but this is just a relatively subtle effect. So it's also the case that none of this has been calibrated at all. just in terms of local populations, but there are some of these insidious effects about resolution that I think are more subtle, and it's important to keep them in mind as well.
And we forget them.
Yeah, or I mean, actually, it took us a while, just talking about actually working on this project. It took us a while to figure out what's going on, actually, because Verja is trying to, we had to combine the Gemini data with the Lijiang data in order to actually get a reverberation lag to get a black hole mass, and she was just getting wildly different numbers, and so then she actually, figured out what was going on, and it was a resolution effect. And for this particular case, one of the, so her paper, she did another paper working on that effect in particular. So her recommendation basically is if you're gonna use low resolution data, because it's a lot easier to get many epochs of low resolution data, at least get one high resolution spectrum so that because you don't expect the width of your narrow lines to change over time. So then you can calibrate it and fix the width of and the relative ratios of your narrow lines and then still use low resolution data. So there are, workarounds like that, but I think just coming up for a correction factor that would be lovely, but I think it's actually gonna be quite, yeah, I think it's more fine. All right, so this is my, this is just a summary of my, the morals from my local cautionary tales. Is just to keep in mind that a lot of these things are probably more complicated than we're actually, than we might be taking into account. So if you think you see a merger with two galaxies, it might actually be three galaxies. And also when you're measuring something like in this particular system, if we think about the little red dots, and the stellar mass here is quite small, the spatial extent on, I don't have the scale bar here, but this is about 0.4 kiloparsecs. So this galaxy is tiny, but you can see the H1 envelope is much larger than that. So when we're talking about seeing galaxies that are physically way too small, if we're just probing the stars, we actually may be underestimating the size of the galaxies. Because of course, at high redshift, a lot of the baryonic mass is in gas. The pathways to the systems we observe in the local universe really affect the evolution. And these systems in particular, I think, are really interesting because with the Higson compact groups, when they were first discovered, cataloged, when Higson did the catalog in the early 80s, basically it was assumed that all of them would merge within a given year. And yet we look at these systems that show evidence that they've actually been in an interacting system for multiple gigayears based on the star cluster populations and how much gas has been consumed. So this is one pathway where you could have a relatively compact system that's actually quite long-lived. What we're seeing at longer wavelengths in the local universe is telling us that if we just have optical data, we might be underestimating or overestimating ages and underestimating masses, and high and low resolution spectral resolution can really affect the masses that we measure in the local universe. So I will stop there, and I'm happy to take any questions. Oh, sorry, are you doing the questions?
No. So I just noticed one thing about the plot about the comparison of HST plus JWST data.
Mm-hmm.
The orange plot doesn't have any emission lines. Were they not included in the fit? Because that would give you drastically different results.
Right. With star clusters, you don't expect emission lines after the first 10 million years.
But then in the blue curve, there are emission lines.
Yes, because this is a much younger star cluster. So the star cluster.
It's not the same object for both.
It's the same. I'll go to the larger version. It's a little easier to see. Yes, so this is, the photometry is the same object. And then there was fitting with the spectral energy distribution of just the HST data, and then SED fitting with the whole suite of data. And when you fit with the whole suite of data, you get a much younger age for the star cluster. So yes, there's really strong pH emission. You see all these strong emission lines, but you only see those in the youngest clusters. So when you get to older ages, you don't expect to see the emission lines.
So my question would be, in the initial FED, why did we not include the emission lines?
Because so actually this U band is very constraining. So this is the Balmer break here, and so the U band emission. I mean, we should to some extent. This is probably a little hard to see, but these are two bands that are quite close together. One is sensitive to the emission lines, and one is not. And you can see that those are offset. But with the uncertainties, they sort of bracket what you see. And then this U band data point is really what pushed it to the slightly older age. But with all of this information, clearly there's emission lines. There's really strong PAH emissions. This continuum is rising. So we have a lot of information here that pushes us to younger ages. But then, so this single U band point is not so powerful. And then what likely happens is that this U band is a little lower than we would expect because we have anomalous dust, which you often see in the youngest star clusters. There's a different kind of dust than what you see in the interstellar medium. So it's really that U band that pushed us there. And I wrote the proposal to get the U band imaging. And the whole thing was about how U band would help us fix all the problems. And then it turns out that, it probably fixed some problems, but not all of them, and created other ones probably.
So the lifetime of a compact group presumably is connected with how extended the dark matter halos of the individual co-orbiting galaxies
Yes.
are. And what are the independent constraints on them? Are there?
No, not really. So so you can do estimates of the dark matter halo mass, but the problem is you only have maybe 4 galaxies. So that's 4 data points is a terrible way to get anything like a virial mass. Some of them are X-ray luminous, the more massive ones, and so you can use the X-rays to constrain the mass. They're not that common, so I don't know of anyone who's done anything like a weak lensing study. So the mass of the dark matter halos is uncertain. One possibility is actually to use the population of globular clusters, since the globular cluster population has been demonstrated to be well correlated, and so that's one possibility to explore. Do that, but yeah, they're not very well constrained.
So your second model.
Yeah. This one?
The younger one has a larger AV.
Yes.
Is that AV doing a lot of optical to submillimeter conversion? Is that what it's doing?
Is it doing is it doing a lot?
Because you could extend the wavelength baseline
To longer wavelengths?
way out, use JCMT.
Right, and figure that out. Is it doing a lot? I mean, we do have, we have the mid-infrared data. I mean, obviously that's not ideal for seeing the conversion for the coldest dust. So we might be able to get a handle on that, but these are not we would never detect something like this with JCMT. It's way too faint.
An AV of 2 isn't very much, right? For when you're really doing these type of things and pushing them out, they're usually AVs of 10, 50, 100. But you're right, it's a global average of some sort.
If you go into the UV.
Yeah.
AV.
Yeah.
AUV is higher.
Right, yeah.
Pulling that down.
Mm-hmm. Yeah. And this shows so if there's no AV, then this spectrum would continue to rise at these very young ages.
Other questions? Okay, not, let's thank Sarah again.
Nobody in the Zoom?
No. Okay. So there might be the front upstairs, so please.
For a minute, then I will check to see if there are any.